Hello everyone, welcome again. Is everything good? Hmm? Your health, your psychology, your courses, your family, is everything is good? Everything okay for you? I hope so, actually. We should start our new class, which is calling least square approximation. I note here it is also known as best approximation in L2 space. I will explain why do we say this is the best approximation in L2 space. But I wish to say guys, the least square approximation is also known as regression analysis, and also this is very popular among applied scientists and also engineers. Okay, so mainly you will use this analysis part, or maybe the approximation, least square approximation, in your experiments later on. Okay, so we are calling it the best approximation because, guys, our main purpose here is to obtain the minimum error. So the main objective will be to minimize our error propagation. This means that you are getting here error is you are getting here the minimum error, which means also that the best solution that you can obtain, possible best approximation, let me say, in your calculation. So on the other hand, we also know that, guys, the thing when we are measuring our vector valued function or vector valued expressions, when we are dealing with the measuring it, we should use some norms. These norms can be the possible choices, as you know, L1, L2, L infinity. So mainly I'm talking about, of course. So we know that in the literature, guys, we have mainly we are using L2 and L infinity norms. So in the literature, we have two options for the least square approximation. I mean the best approximation. Best approximation in L2 norm, best approximation in L infinity norm. Today's topic will be related with the best approximation in L2 norm. For this reason, our error propagation will be measured by the 2 norm. Okay, but when you are dealing with the L infinity norm, this is also possible. Okay, it is also it's also used in mathematics also, but it is called as minimax polynomial and mainly used in finite element method. For this reason, we are skipping in this undergraduate classes, we are skipping to give here the minimax polynomial. We are just dealing with the L2 space case, which is calling regression analysis. Okay, so you need to know this thing as your culture. Okay. As I said you here, today's topic will be best approximation in L2 space. So L2 norm will be used, and our main aim will be here, obtaining minimum error. So to do this, this end, we should give here, we should separate ourselves into two classes. Okay, the first one is linear regression, which defines here our general theory behind the least square approximation, and the second one will become linearization of the nonlinear data. This does not mean that nonlinear regression. We are considering just, guys, nonlinear data set. Okay, it means that just your data set, your experiment gives you nonlinear behavior, but it is not meaning, this does not mean that you are doing here nonlinear regression, because nonlinear regression is very complicated, guys. So it's also recently is also studying on this topic, so it's a challenging problem. For this reason, we don't give here nonlinear regression. We just give here if our set is not linear behavior, does not have the linear behavior. If our set has nonlinear behavior version, then what we will do here. Okay, so one more thing I need to say before starting to theory. Guys, recently the artificial intelligence is very popular among the applied scientists. Okay, so maybe you are also dealing with this concept. I should say here, in the artificial intelligence, actually, we should classify our problems into two classes. The first one is regression, the second one is classification. So the regression mainly takes here like the least square approximation. On the other hand, also we have the artificial intelligence in the the package version I'm talking about. You will learn for feedback of the artificial intelligence in progress, as you know. It uses backpropagation algorithm. The backpropagation algorithm takes also the same basis that we are discussing here, the theory, the same theory. Okay, they are taken the basis. Okay, so for this reason, I have given here everything, every cultures for you when you are considering the best approximation and how is the relation between the least approximation method with our experimental studies, or maybe with the relation between our least square approximation and the many main methods in the universe which is recently used, like machine learning or artificial intelligence, like this words. Okay, so we are now ready to understand the theory of the linear regression. First of all, I want to give here as a reminder for you guys, in the linear regression, do not forget, even though I'm writing here like regression, don't forget this one, please. We are doing here again an interpolation. So the interpolation, helps us to approximate your data set, okay, by using some polynomials. Today, we will start with linear polynomial. But what is the difference between our new method and also the previous ones? The thing here, which is the most important thing for us here, is to get minimum error. For this reason, we should define here our error propagation, how we can find out the error. Okay, so here is the error in mean square case we are considering, or because we are dealing with L2 space, you can also consider here just only square versions of the addition. Actually, in the L2 error, 2 norm, defines us here the square root of, actually, it is also giving the 2 norm actually gives you here all approximation, okay, let me say app minus exact one in square and taking the square root. Because we are dealing with here, guys, the minimization or maximization of this error, you need to also discuss here. As you can skip here the square root of this function, because if you minimize the inside of the expression of the square root, it directly minimizes your total expression. Okay, for this reason, actually we are just dealing with the inside of the expression, that's all. So we know that here, this is that we are doing in all general, we are subtracting to measure here the error. You are subtracting your approximated values from your exact values, if you know it. But do not forget, here we don't know what is the exact value or what is the exact curve which fits your data set. You are just approximating to that data set, but you have some experimental measurements. You are considering conducting here an experiment, and totally you have learned here, you are obtaining some data set which is corresponding to, here you have your x0 point which is corresponding to y0. For this reason, we are considering here some experiment instead of exact. You may say that experimental data and minus approximated data, like this one. Okay, here, because we are dealing with here the linear regression, we just try to find out here the linear polynomial. Okay, so the linear polynomial, general linear polynomial, can be defined as in that form. Okay, guys, From now on, now we are ready to define the error of this approximation. So when we are calling the error in mean square case, okay, mean square error I mean, we are considering here polynomial. I wrote here 1. It is like your degree, okay, because our degree here at most, 1, first order degree, first degree polynomial we are dealing with because of the linearity. So you will write down here P1 xi because component wise, guys, we are having here some components. For this reason, at the value of xi, which gives me my approximated value, and f of xi, which gives me my experimental studies answers, okay, the results of experiments, for instance. So you will measure here in square version, and this is obtained as your R. Here is, I can define here like R. Okay, this is our error definition. Okay, now it is time to create here turning our attention to the main problem. Our main problem is to describe here the minimum error, right? So the minimum error or maximum blah blah means that in mathematics this is like an optimization. You should consider here the optimization. It's converting to an optimization problem, as you know. So we should minimize our error function, but do not forget we have here totally two unknowns. We don't know what about here A1 and A0, such that my error will be minimized. So this is the thing that you need to reply that question, okay? It is main objective for us. For this reason, we consider here to handle with the optimization problems, guys, you have learned from Calculus 1 and Calculus 2. It is turning to the derivative process. So in Calculus 1, we have discussed the single variable functions. For this reason, just taken here one derivative, first derivative, with respect to our unknown variable. But here, we have actually two components which are unknown for us, okay? It means that you will deal with here, you will deal with your unknown variables will be A1 and A0. You need to discuss them by considering the derivatives. So it is turning to the knowledge that we have given to you in Calculus 2. Maybe you may say here the gradient, or maybe you can say that to me like the derivative of several variable functions, okay? So we are defining here, you know that I have also written here knowns and unknowns for you, for your understanding. Okay, so we will take here our derivative of E, the error approximation, with respect to A1 and with respect to A0. So these are important because, guys, we are considering them as our problem because they are considered as here are unknown variables. Do not confuse with your x variable. In Calculus 1 and Calculus 2, we mainly write down as the x values with respect to x, with respect to y, but they are unknown therein. Now our unknowns are A1 and A0 instead of x1 and xi and yi's, okay? So please be careful for them. Okay, by taking here the derivatives, and we have observed that the right side will be 0 because of the optimization problems. Okay, so here I should complete, before giving a break, I should complete here my total theory, then I will give a break to you. Okay, guys, now we are considering here the derivative of E, error, with respect to A1 will be 0, and also this is also similar to a 0 case. So we are writing here taken the derivative. Do not forget you have taken your derivative with respect to A1 or A0. So the derivative of A with respect to A1 will be here xi because it is like a coefficient. So I'm writing here, I'm trying to teach you because we are just doing, asynchronous education now we are doing. So maybe you can have some questions because of this I tried to explain what we are doing. Okay, with respect to a1 means that this is now a coefficient for me, and with respect to a0 now the coefficient is like 1, so for this reason here is I multiplied by 1. So if you are rearranging your expressions, I mean here, do not forget guys, here is 2 times or 2 divided by n plus 1, because the right side is 0, it is nothing for you. So this x will be distributed in all your parentheses. So by rearranging the equations guys, one can observe that here your expression. Okay, you need to know this is an important class for us. This is our important decision actually. So from now on, you have an equation, 2 equations actually, with 2 unknowns. It is actually enough to solve your problem, because 2 equations, 2 unknowns means that you can find a unique solution according to a1 and a0. So for this reason, I'm setting my equation in the solvable version. So what does it mean? It means that knowns and unknowns, you can separate your knowns and unknowns, respectively. We are considering here a1 unknown, a0 unknown. So on the left side, we have learned that here my first equation can be put into that form. And also the second equation can be also put in the similar, by using the similar way, you can find out here your expression. Generally guys, I should explain this one. This is important because for me, generally the students are confused about the summation of 1, but do not forget, it is just adding here 1. How many times? It is up to your data set. How many points do you have in your set? Means that this time n times n plus 1 times 1 will be added to each other. That's all. Okay, totally guys. Here I note actually, guys, I know this one, but because of you need to see here the relation between here our numerical methods with the linear algebra session. So you should see here, we have here 2 by 2 system which is solvable. And one more thing I need to say here, when you are dealing with here, when you are taking your polynomial like linear polynomial, then it is turned into 2 by 2 scheme, because you have here obtained here 2 unknowns. But what if you are dealing with quadratic version or cubic polynomial? So you will do the same analysis, but if you are choosing here quadratic, for instance, so you will have here a2, a1 and a0, which are your unknown. So you should do here the minimization, or I mean the derivation version will be extra. You will have here extra one more equation, which is del E over del A2, like this one. So the analysis are so similar to each other. It's up to the choosing your polynomial. So for this reason, in this process, I mean 2 by 2 version, you can use the elimination. Okay, it's acceptable. But what if you are using here cubic polynomial, quadratic polynomial, or so on? If you choose here, if your polynomial degree is getting increasing, so means that your dimension is also increases. So it means also that you should use here, you should benefit from here linear algebra. For this reason, I'm giving in the linear algebra version, as you can see in this slide. So up to here, let's have a break. Up to here, I have completed here the theory of the linear polynomial, but do not forget, I need to mention about one more time. I need to mention about it. Once we are choosing our expression polynomial, then you should use here your analysis will be in the similar way. So your proof will follow the previous one I'm showing here. And you will create here n by n or 2 by 2, 3 by 3. It's up to your degree of the polynomial, you know. So you are creating here an algebraic system which is solvable for your method. And you will try to find out your coefficients of your polynomial. That's all. So let's see an exercise in the next video. See you.